I'm so glad that wasn't recorded.
You jamonk.
Okay, so we're gonna get into chapter 13, okay, where we're talking about reinforced concrete. The discussion from Tuesday is not gonna be posted for a little bit. I wanna wait since we went over the midterm. The independent study students are taking the same midterm. They're a little bit behind, getting caught up on the material. So once they're all done with the midterms, I'll get that posted. So, but as far as from homework stuff, we're not gonna really see anything that's gonna impact us for this next round of homework, so. So chapter 13 deals with reinforced concrete construction. We've talked about concrete, talked about it last semester. Those of you who have taken materials one are familiar with it, but there's some terminology, some things that we need to look at. And so let's remind ourselves, what are we dealing with when we talk about concrete? What does the book give you as your ingredients?
Aggregate.
We have our aggregates, right? Water and cement. Portland cement, yep. Did they mention anything else? It's kind of all they really touch on, right? But we have to be aware that in today's age, okay, in 2018 and going on, there's a lot of other things that we use, right? So we have we've talked about SCMs, supplementary cementitious materials, okay, so our fly ashes, our slag, our silica fume, okay, and then we have admixtures. Okay, these can be our air entraining agents, our water reducing agents, corrosion inhibitors. There's all sorts of things available to us. For the purpose of this chapter, when they talk about reinforcing, they're talking about steel. But keep in mind that another admixture that we can use, of which I only have any polyfibers, but remember that we also have fibers that are available to us. And that's what we'll look at next week. I've got nothing but radio silence from Van Sickle Allen. If you guys want to look at these fibers at some point, whole bag's full of them, but just a little, maybe an inch and a half, maybe they're 2 inches, but just various fibers. And that's what we'll look at. So I'm banking on not having Van Sickle Allen here next week. So we'll see how far we get today. Whatever we don't get to in chapter 13, we'll wrap up on Tuesday. And on Thursday, we'll do some lab work. So what we'll do is we'll cast some beams, cast the deep beams, the 6x6s. We'll do a straight cement mix. We'll put some fibers in, and then we'll have some with reinforcing steel, and then we'll cast some thinner members. On Friday, I'll come in and strip up. Well, maybe we can strip them the following Tuesday and get them into lime water. And then we can test them on Thursday at 7 days.
If they're still here.
We'll leave them in here, so we'll have much tighter control over them. So
Do not touch sign.
yeah, exactly. So we should remind ourselves, and we've talked about it already this semester, but what type of axial force does concrete do well in? It does very well in compression, right? And it does poorly in tension. Okay, so the portion of this chapter that they're focusing on is how do we reinforce and why do we reinforce? Okay, so they go into talking, the majority of the time is about tensile reinforcement, and that's all that we are really going to have time to focus on. It's still a fairly involved process to figure out our tensile reinforcement, so just be aware that there is also compressive reinforcement that's used because of the fact that steel has fairly high strength to area ratio. Okay, so you can get a lot of compressive strength for a small area where we need a larger bulk volume from our concrete. Okay, so and then they talk about how we place concrete. And we talked about this a little bit last semester in the Materials 2 class, but how does this book lay out how concrete can be placed? What are the 3 different types that they mentioned?
Precast.
Precast?
Cast in place, and,
Well, that's like that. Don't they call it that?
Right,
Oh.
and that's what I want to mention.
post
And what's the third item that they mentioned?
CMUs.
CMUs or masonry construction, right?
I don't know. Did you read this?
What's the difference between these two? What's the difference between cast in place and site cast? Do you remember from last semester?
Cast in place isn't gonna move, site cast we can move, is that right? Like-
Yes.
Cast in place in a
Exactly.
final
Like,
position.
Yep, yeah, so remember everything that they were doing when we went out to the legacy. They were doing cast in place, right? So they were moving the forms up the building as they were going, okay? An example of some site cast work, the bridge at FIU that failed, that was actually site cast, or the deck panels for the Franklin Avenue Bridge that I discussed on Tuesday. That was also a site cast project, okay? So I just want to make sure that we're aware of that distinction. They're kind of using site cast interchangeably for either of these operations, and it's not truly technically correct to discuss it that way. Okay, so we talk about our strength of concrete. And so what are the major items that they talk about as far as how we can impact the strength of our concrete? What's the biggest factor that drives? Our aggregates, right? Remember that our aggregates comprise about 80% by weight and by volume of our concrete. Okay, so that's a large percentage of it. And for the longest time, aggregates were just used as filler. We just needed it to take up space. And about 50 years ago, people started doing research and discovered that if you increase the quality of the aggregate, you increase the quality of the concrete. So now that becomes a very important factor in determining what we're going to use for our concretes. Is a lot of quality testing goes into the aggregates themselves. Okay, not only their properties, but how they interact with cements. What are some other things we need to be aware of?
Additives.
Any of our additives can impact it? Yep. Okay, so we can add air entraining agents, right? That will lower the strength a little bit, but it helps our durability. Okay. What about anything else?
How it's cured.
How it's cured, absolutely. Curing conditions are vital. To our concrete. It's another thing we can control.
Yeah,
The water.
Water cement ratio. Okay?
So you said the aggregate, like the size of the pebbles are for different strengths? Is that, because like we would use, I was pouring concrete, but we had the customers, and it's like, hey, I want the little tiny aggregates because they wanted exposed, you know, like after you finish it and then you spray it
Sure.
off, you know, because they wanted that look, you know what I mean? And they were
Yep.
doing this on like a pretty big patio, you know, so like.
So from a patio, I wouldn't be concerned about the strength component of your aggregates.
Okay.
That much. There you're looking more at a finish
Yep.
aesthetic, right? What we're talking about when we're talking about quality of aggregates, we're more interested in what's their durability going to be. So mechanically, how do they break down? How do they break down in the presence of chemicals? We're interested in spacing. Spacing would be a huge factor for us, and we'll talk about this in a little bit when we talk about selecting steel sizes. So the code has requirements for you can't have, well, obviously you can't have smaller spacing than your largest aggregate, but you have to have a factor of 3 greater than your largest aggregate so that all your aggregate can get through that steel. Okay, so perfect example of that is, well, we can pull this up quick. I got some pictures from the St. Croix crossing project, and their closure pores, because of
What's the St. Croix crossing?
St. Croix Bridge.
The Stillwater Bridge?
Yep, Stillwater, yeah, Stillwater crossing. Because of their reinforcing schematic on the closure port, they couldn't use anything larger than a 3/8 inch aggregate.
I don't think I could eat if I was
Probably a bunch of leftovers around.
I probably could have found something mixed in with some diet food.
Yum, yum.
Like some chocolate bars.
pretty,
Where'd we go?
You probably would've hurt your stomach.
exactly.
Yeah.
So-
I was,
Because of this reinforcing schedule, not so much over here, but you see right in here, it gets quite congested. Okay, so they couldn't use a 3/4 inch egret, they couldn't use a 1 inch or an inch and a half. So there is sometimes those considerations that get taken into place.
Are those
And-
stirrups?
No, these, so here I'm standing on the deck,
Looking down.
that's St. Croix River right here.
Oh,
Okay, so we have one of the box girders, and so they've got the reinforcing steel coming out and
Yeah,
it's
I
hooked.
see it.
So, and so then you have your box girder for the other side. So then to make it a monolithic structure there, they were joining those sections together.
They've engineered it differently as far as having stronger concrete, probably spaced the rebar wider. I guess I don't know how they fix that type of thing.
Space the rebar wider.
Bigger,
From a
stronger-
structural standpoint, that's outside of my area of expertise. You maybe could have. The problem, I think the problem that they're gonna come into is you need a certain amount of development length to get the strength. They're increasing it with the hooks, okay, because instead of having just this much development length, now they have that much development length for their rebar themselves. You can reduce your development length a little bit by increasing the strength of the concrete. But it gets to a point of diminishing returns, such as it is. So I don't know the specifics for this particular project, how they got to that point. But yeah, that is a good question, Greg. Okay, so, does that kind of cover your question on aggregates,
Yeah.
Rush?
This is because every time we did like something more structural, it seemed like we were using the big ready mix bags with the bigger aggregate.
Yep,
You know?
and you have to remember, there is an ASTM standard for a specification for aggregates to be used in concrete construction.
Okay.
And regardless of if you're using it for patio construction, foundations and columns for a structure, for a massive structure, those aggregates still have to meet those requirements, okay? So, so when we think about our quality control, what are some items of importance in quality control with concrete? What do we need to be mindful of? We talked about the curing conditions, right? So that's certainly still a factor of importance, but where does the concrete oftentimes come from? When we're working on large projects, where are we getting it from? Sometimes we're mixing it on site, right, if we're doing a smaller project.
From-
Ready mix plant,
Yeah.
right? So what does a ready mix plant need to be aware of?
What is being used for?
Yep,
The conditions it's being going to.
purpose of the mix. What about the trucks themselves?
How far they're traveling?
Yeah.
Yep, travel distance, travel time,
So would weather come into that too? I mean,
absolutely.
that, you know, they got it, the temperature because of the
Yep,
cement.
yep, temperature absolutely gets taken into account in the summers. Trying to remember what project I was down on in Iowa. It may have been for the dam in Pella. Anyway, ready mix plant brought in a semi-trailer once a week full of ice, and that's what they use for their water source. So they paid a guy all week to stand up there, tear open bags of ice, drop it onto a conveyor and conveyor it into the plant, okay? Just like in the winter time, they'll use hot water, okay? And then we can use accelerators and retarders as additives to help speed things up in the winter time or slow things down in the summer. When they talk about this Portland cement, we do truly have 5 types that are available to us. The only types that they really mention are general use, which is probably what you'll see on 90 to 95% of the projects that you work on in the Twin Cities area, okay? But we also have other products. We have sulfate resistance. We don't really need to worry about it here in the Midwest, but once you get out to the Rockies and beyond, they have elevated rates of sulfates in their soil. So they need to make sure that it's not reacting with the cement chemistry causing expansion. So, and then we also have high early, where they take the cement and they grind it a little bit finer. So those smaller particles take up water faster, it hydrates faster, it also typically generates a little bit more heat. So, but the high early and the general use is what they talked about. So, what about on site? What do we have to be worried, well, not worried, what do we have to be concerned with from a quality standpoint?
Pumping?
Pumping could certainly be an issue, yep. Could be distance,
Height?
could be the geometry, could be the height. The Trunk Highway 36 bridge project, that was the last major project I did at Braun. We tried and tried and tried to figure out how we could pump onto that bridge deck, and we just couldn't do it. We couldn't do it with the mix. It couldn't both meet the requirements that the state had and be pumpable, so they conveyored all of that concrete onto the bridge deck. I wasn't up there for much of the pours. I'm sure it was a huge pain in the rear end to place concrete, to place that much concrete with a conveyor. So, yeah, that's absolutely is pumping gets to be a very big issue. What are other things that we need to do? It's something that we always have to do with concrete. Well, I shouldn't say always. We don't have to do it with self-consolidating concrete, but conventional concrete. What do we always have to do once we get it into the forms?
Spread it.
Finish it? Level it? Yeah.
Scrape it.
Scrape it, level it, some sort of consolidation and finishing, right? Okay, so we have to be aware of our consolidation.
Make sure it cures correctly.
Yep, we have to make sure that our curing conditions are met.
Wouldn't that be
Keep going
quality
through the
control
market,
too?
man.
Yep, absolutely. What's that?
So keep going through the market.
Yeah, exactly.
End class early.
Let's see, what was I saying before curing conditions?
Consolidate.
Consolidation, yes, thank you.
Finish.
Too damn.
Consolidation, then we have our finishing. And we again have curing as a portion of concern for us on site, okay? One thing to be mindful of, especially with these SEMs, if you're working with specifiers or if you're doing specifying, be careful. Typically people are going to be specifying a 28-day age test for acceptance. If we're starting to look at things, especially if we're doing massive structures, if we're doing dams, if we're doing anything where we're using a lot of these SEMs, by a lot I mean 25% or plus or higher of fly ash and about 30% plus of slag, I would recommend that you push your strength test out to 56 days, okay? You can still perform a test at 28 days, and if you get that strength, that's great. But we have to remember that fly ash and slag is a secondary reaction. Okay, so the Portland cement is going to react. The byproducts of the Portland cement create something that the fly ash and the slag can react with. Okay, when we start putting in massive amounts of these materials, we're going to slow down our strength gain. Okay, so just be aware that sometimes you may see 56 days on a project. Now, what does that mean? Does that give us a cause for concern? How long is 56 days?
Forever.
It's 8 weeks, right? What are we doing 8 weeks after that? We might be done by this time, right? But be aware that the ready mix plant, they've done extensive testing. Okay? The lab that's done testing on this, we've done extensive testing. Okay, so there's all kinds of ways that you can monitor this in the field. We can drop temperature sensors into the concrete. There's a lot of ways where we can keep track of this thing. We can know something within the first 2 or 3 days if it's trending properly. Okay, by the 7-day test, we should know if there's going to be major cause for concern. So, okay, so that covers that kind of stuff. The next major property that they talked about is stiffness. Okay, and we've talked about that, right? What are we referring to when we talk about stiffness?
How much it's gonna bend?
Yep.
Okay. That's a question.
This is also, remember when we talked about our modulus of elasticity? Okay? There's a reason why we did those calculations. We're concerned about this not only with steel, we're concerned about it with wood and concrete as well. So we're interested in, as we load our columns, as we load our beams and they're deflecting, how much of those deflections are they going to be able to take where they're going to be able to go back to their original shape so that we don't have what happened down in Florida last week, right? Down in Florida, they exceeded that modulus elasticity. They got out of the elastic zone into the inelastic zone. The concrete was not able to recover. Very tragically ended up in failure where people died, okay? So it's something that we're really interested in. Typically speaking, from a calculation standpoint, from a design standpoint, they start out by saying the modulus elasticity equals, where'd you go? W raised to 1.5 times 33 F prime C, also to the 1/2. We don't have to worry about this portion, and we're not going to do any design. I just want to make sure that you're aware that from a design standpoint, what we're talking about is 57,000 F prime C. Okay, that's what the structural engineers use in coming up with this modulus elasticity. F prime C is our design strength of concrete. Okay, so typically going to be 3,000, 4,000 psi. From the standpoint of evaluating a mix, a calculation is not sufficient. Okay, it's a test that we have to run in the lab. It's very similar to the compression test where we take the cylinders and crush them. Rather than actually crushing them though, we deform them about 0.05 inches. Okay, so 1/20th of an inch. Measure that strain, cycle it over and over and over. Okay, so we measure as we're compressing that 0.05 inch, how much is it expanding, okay, in the Y dimension. And then we actually determine that number. So at ASTM, we just got done doing a round robin study because the data that we had was good for concrete with a compressive strength of about up to 9,000 psi. No one's interested in modulus elasticity of concrete that's 9,000 psi or less. Okay, we're doing it at 12,000, 16,000, 20,000 psi, so everything had to be redone. So that machine that we bought, well, long-term we'll be able to run modulus elasticity. It's just getting the equipment so a little lower down on the scale of importance currently. So, talked about creep. Okay, creep is also relaxation of our concrete. Okay, it's not talking to any specific personality of the concrete itself. As this concrete is sitting out at a structure and we start compressing it, it's going to continue displacing. Okay, and we're interested, think about a bridge. What's going to happen? Think about the St. Croix crossing, the Stillwater Bridge. If we don't know what that coefficient of creep is, and we aren't monitoring it and determining it for that mix ahead of time, what could happen to that bridge? Keeping in mind that it's a bunch of segmented boxes cemented together. If it starts creeping excessively,
When it get all deformed.
yeah. If you've seen the project, it's curving, it's running, it's changing elevation. We'd have all sorts of issues. We could have joint failures. We could end up with a box section falling into the river, pushing out into the landmass, etc. So, but people would not be very happy with it. Okay. And then the last component that they introduce, and what we're going to focus on, is the reinforcement. Or what, I should say what we're going to focus on today is reinforcement. And so again, Rush, you might get your wish.
Keep writing.
So for the purposes of this chapter, again, we're talking about steel. Okay, so we're talking about steel bar.
We're willing it.
And remember from the question, Kyle certainly remembers it because he emailed me about it, but what is unique about this bar? What do we do to this bar during the manufacturing process? It gets deformed, or we put something on the surface, right? We don't want nice, smooth bar. What's going to happen if we have nice, smooth bar that we put into our concrete?
It's not going to bond, right?
It's not going to bond with the concrete, right? As soon as that concrete gets put into service, it's going to slide right along that surface. Okay, so we need some sort of deformation. We need some sort of surface additive. increase that bond. Okay? Getting back to the stiffness. Do you remember what the modulus of elasticity is for steel?
32
32 million? No.
29 million, right?
I was gonna say 30,000.
What?
Well, you were thinking in KSI, right?
Yeah, see,
Yeah.
I learned those.
Don't lie.
I did. I just,
So typically our modulus elasticity with steel is about 29 million. We do not see that high of a number with our concrete. We're probably seeing 9 million, maybe 10 million, maybe 11 million. Kind of the limit of what we can produce currently. Okay, so not only is this great for us in our tensile reinforcement, this is great for us for columns as well, or walls, right? So and think about it from an economic standpoint. Do we want to have big, bulky walls and columns, or do we want to make them as small as we possibly can? We want to trend as small as we can, right, to save on money. So as we make our columns and walls smaller and more slender, they're going to tend to want to buckle, okay? Or if they're in some sort of wind load event, seismic event, they're going to tend to want to twist, okay, so get into torsion. Okay, so this helps also, helps in buckling and torsion. Of our columns and walls. Okay? I don't need to write columns and walls twice, right? Okay, what else do we want to say? We want to talk about cover. What is cover? What are we talking about when we say cover?
Cover from the elements?
We need to protect our steel, right? What happens to our steel if we don't provide protection?
rust.
It's going to start corroding, right? It's going to oxidize. Okay, so there's another thing from an engineering standpoint. Materials engineers need to be aware of not just that we provide sufficient cover, but that we are able to reduce the porosity of our mixture sufficiently so that we don't allow migration. Okay, so there's a lot of testing that we do on mixtures, on any additives before they get released to the public for common use. Okay, so.
And when you say cover, does that just mean like you're covering it until you're ready to
No, I don't
use
think
it?
he means poly.
No, so, good question, John. So cover is, if we're looking, so we're looking along the length of a beam, okay, is what we have, so it's running into the board and it's coming out towards you as a class. We can't have our steel resting right on that surface of that concrete. And typically what we use for design is 1.5 inches for beams, and about 3/4 of an inch for walls. Okay? Now, depending on, this isn't a hard and fast rule. Okay? We may find that based on environmental conditions, based on the geometry and the amount of reinforcing that goes in, we may need to increase these. Okay? But generally speaking, from our initial design standpoint and for the homework that you're going to be doing, this is what you'll use for your cover. 1.5 inches for beams, 3/4 of an inch for walls. Okay? So, it's a good question. Yeah, it doesn't mean that we just provide that while it's curing. It needs that protection throughout its life cycle. So, from a life cycle standpoint, we have to be aware of this because remember, what is the steel doing? Predominantly speaking, providing what type of reinforcement? Providing tensile reinforcement, right? What do we also know that concrete is always going to do? always going to crack, right? And the purpose of the steel is not to prevent it from cracking. The purpose of the steel is, if it cracks, don't let that crack cause failure. Okay, so from the life cycle, we do need to be aware of, and you can see it on bridges throughout the country, that it gets to a point where this cover will start degrading. Once it starts degrading, we begin having exposed steel. So I was talking about it with the other two instructors who teach statics yesterday. I looked it up last week, and it seems like it's a huge number. But it seems like when you think about it, at least to me, it seems like a very small number. To bring all of the bridges in the United States up to structural competency would take about $123 billion. So yes, $123 billion is a lot, but when you think of the number of bridges that we have, it is still a large number, but.
Well, how long would that last?
What's that?
How long would that last? You know, because they got like a life cycle, so like.
Correct.
You know what I mean?
Yeah, that I think is probably looking at just rehabilitation, probably
Yeah,
not
'cause
looking
when-
at replacement. So
when
you're
they-
probably looking at 10, 15, maybe 20 years.
When the bridge failed here, I remember it was like the whole country turned inward and started looking at the
Mm-hmm.
bridges, and we failed infrastructure test or assessment. We were like 60% of the bridges
Mm-hmm. Yeah,
won't
the-
pass
Yep.
right now.
Yep, yeah, so the American Society of Civil Engineers gives a score every year, and I think it's been D+ for
Yeah.
a good decade and a half or so. So,
Nailed it.
yeah, but. Okay, so that covers, no pun intended, I guess. And then the last item that we want to look at, actually, that's not true, we got two other items to look at. So we also have
Down to one.
Down goes Frazier.
I hope that red's just burnt.
I think I have one more marker in my bag.
Settle down. That wasn't part of it. Ah! Son of a. I'm gonna come here after class and just keep marker caps off.
Take the cover off. And
Yeah. Come in here before you get your put back on and just sabotage your class.
Right. Why would spacing of bars be important to us? What do we want to? What are some big?
Just distributes for the when the loads on there, distributes the strength.
Yeah, we want to distribute the strength, right? We want to make sure that we don't have areas of unreinforced concrete, right? And then what do we talk about? What about the concrete itself? What happens if we aren't mindful of the spacing of our bars? What could be a problem that the concrete could experience? Yeah, if we aren't able to push our aggregate through, right? And then we no longer have a concrete, we have a mortar that's pushed through, and then we have a bunch of rocks just sitting all over, right? Okay, so we want to make sure that we can pass concrete into our forms. Okay, and then the amount of steel is the last one. Why is it important to know the amount of steel?
So you don't have too little?
Yeah. We need to know the amount.
You mean the number of bars? You're talking about the size of the rebar itself.
You ask the question, but
Both.
the question sound like you're wrong.
Okay.
Well, exactly, yes. So the first step is figuring out how much steel do we need?
Like the grid.
Well, even before that, we need to figure out total area
Okay.
of reinforcing that we need. Then we need to figure out, given the limitations that we have, how wide our beam is, how much cover we have. Then we can look at our selection, right? So, and that's a portion of the assignment that you're going to have is looking at beams and seeing, okay, once we determine the area of the steel and we know the limitations of the beam width, what type are we going to select and place? Okay, so.
That's all, when you're saying steel, there's no, you're only talking about the rebar, right?
For the purposes of what we're going to be
For
looking at, yeah,
concrete.
we're just talking about rebar. Yeah, we're not taking mesh into account, anything like that.
Okay.
Yep, yep. As far as shapes and sizes of the bar, refer to table 13.1 on page 400 of your text. That gives you, that's gonna give you your common diameters, and I think it also gives you cross-sectional areas.
Cross-section.
Yeah, it gives you cross-sectional areas. It also gives you unit weights. I don't think that we're gonna have time to look at any calculations from a density standpoint, from a weight, what it's contributing for that. I think all that we're gonna be able to get into is really determining the area, the size of the bars, and the number of bars that we're putting in, okay? So, the last thing that they look at before they get into the actual problems themselves is the strength calculation numbers. Okay, so up until this point, what we've been doing is we've been drawing goofy situations, right? We've been making beams and we've been making trusses and we've been putting different loads on them and calculating things like axial loads. We've been calculating bending moments, we've been calculating shear strengths, right? That's what we've been doing up until this point. All of those numbers are used from a design consideration to determine how we size these things, okay? So that was the whole purpose. And 13.2 gives you those considerations. So you just need to be mindful of what the type of problem is asking you, which type of reduction it is that you're going to use. And the major one for us is that we're going to be looking at 0.90. Okay, so 0.90 is what we use for flexure, it's what we use for tension, it's what we use for compression. Okay, so once we determine the maximum load, given the conditions, we'll divide it by that 0.9. That'll tell us the condition that we need to meet. Okay, and that'll make a little bit more sense when once we get into a problem itself. So maybe we'll see. So once we get into 13.3, which I think is really about all the farther we're going to be able to get. 13.3 gives us the ultimate strength. And we start out with something that we're very familiar with, right? We have a beam. We've got two reactions, and we have forces, right? And so what they lay out is they're going to go a certain distance, and they're going to cut that beam, okay? And we're going to call it that it's X feet away, right? So we're familiar with all of this up until this point. What happens when we cut this beam? What do we now know we're going to have to take into account?
The length of the beam, the new length,
Yep. What's the reaction going to tend to do out here?
okay.
It's going to try and put a bending moment on there, right? What else are we going to have right at this end of the beam?
No, if you cut after this reaction, wouldn't it be negative?
Wouldn't what be negative?
Wouldn't it want to rotate down because it's no longer got that reaction? You had two reactions, look where you cut
The
it.
beam itself?
Yeah,
Yes, out here I would agree with you that it's going to try and bend like
the other
this,
way.
right?
No. Where's,
Oh, I see what you're saying. To meet
From-
equilibrium.
from R2, let's say, right? It would rotate down because you no longer have a reaction over here.
From R2 it would rotate
The
down.
right one.
From here.
Yeah, wouldn't it rotate negative, counterclockwise?
Yes, I would agree with you that at this point,
Yeah.
your moment has to be in this direction to meet that, to keep you at equilibrium.
That's not what Rush is asking.
No. You get what I'm saying?
Yeah, he's taking the left side of the cut, Rush, not the right side.
Oh, okay. Okay, I got it.
What am I not understanding?
I thought you cut where X is and got
Yep.
rid of the left side.
No, sorry, I'm looking at this portion.
Okay.
Sorry.
I got you.
So if we look at this beam and we think that we have reinforcing steel running along in this direction, what else are we going to have right here at the end of the beam? What did we determine before we did our bending moments? We're going to have a shear force, right?
Any question?
It was.
It sounded like a statement. So, but yeah, we have shear, right? So we also have a couple other a couple other things going on. We're going to have a tensile force, right, from that reinforcing steel. We're also going to have a compression force, okay? And we'll call the tension force T, we'll call the compression force C. The compression force, that's the force that the shear is exerting on the concrete itself.
What words come to me?
It's also being pushed back on by the force of the steel, okay? If we look at C and T, they're separated by a distance. So what are they going to do? What do forces do when they're separated by a distance?
Rotate?
They're going to cause rotation, right? This force is going to try and rotate this direction. This force is going to try and rotate in this direction, okay? If they're at equilibrium, we won't cause our beam to fail, okay? And this is what we're going to look at. We're going to set this up and to allow us to figure out what area of total steel do we need, and then from that total area of steel, we can figure out how do we need to size this beam, what type of bars do we select, okay? Does that make sense?
So if you figure
Vaguely?
if you figure the steel out right, it'll be equal to the C and create equilibrium?
Correct. Correct. So, and if we get it to the point where T just equals C, that will be the most economical, okay? That will cause us to need the shallowest beam and the least amount of steel. Now, because of the geometry, maybe this thing needs to be 14 inches wide, okay? Because of our geometries, maybe we aren't able to get T to just equal C, maybe it equals 2 times C, okay? We're fine with that, as long as this isn't less than that compression force, okay? And what they go on to show, and if we really wanted to look at it, we'd have to look at calculus, so I'm not going to send us down that rabbit hole, but essentially what you do is you take that compression force, that F prime C, and you section it out over that entire system, and you figure out your block. But all that we're going to concern ourselves with in setting this up and figuring out our equations is we're now going to look at this system as, just like we did with our uniformly distributed. Okay, so this is occurring at a point A inches from this surface. Okay, or I'm sorry, that's not correct. This distance, okay, the face of the compression force is A inches from that top surface. Okay, because it's uniformly distributed, what do we need to do with it to make it a point load?
Divided by.
We need to put it at A over 2, right? Our steel will be located at a distance.
Would it always be A over 2 though? Wouldn't it be?
It wouldn't always, but for the purposes of what we're going to do in this class, it'll always be A over 2.
Okay.
We're going to assume that it's uniformly distributed. But yes, Rush brings up a good point that we are not always going to have cases where it's going to be uniformly distributed. Okay, so, but for what we're going to do, we couldn't figure it out other ways unless we were using calculus. So it's nothing personal against anybody. We don't have the time for that. So how far are these two forces apart from each other?
D minus A?
Not D minus A.
Oh,
What's that distance?
D minus A over 2?
D minus A over 2. Okay? Does everybody see where that distance is coming from? And what its magnitude is? We also know that our tensile force, what units is the force in?
Pounds?
It's in pounds, right? So how could we figure out what this force will be? What could we use?
So,
We need two items to get to our force. What can we measure on our steel?
the area,
We could measure the area of the steel, right? What unit is our area in?
inches.
Inches squared, right? So what could we multiply our area by that will give us a number with units pounds?
29 million.
Yeah, we could. We don't necessarily want the modulus elasticity here, but we do want something with PSI.
So would you use your area and then you look at,
What were the type of strengths we were interested in when we talked about steel? There are two strengths that you were asked about on the midterm. Do you remember? The true or false
Tension.
question. Not tension.
So,
No.
what's another one?
Remember when we pull on steel,
Change in length?
it's related to it.
Elongation?
Elongation?
It's not the elongation.
Tensile?
What if we use the yield strength?
And I
Remember?
would have never got to that.
No? Okay. I kind of got that feeling. So.
Yeah, just throwing one, see what's
Yep.
stuck to the wall.
Yep, that's fine. So, would we want to use our ultimate strength?
No, that's where it,
What happens if we use ultimate strength?
it'll never go back.
Yeah, we are going to get elongation, as you guys mentioned, right? We don't want to see significant elongation, right? We want everything to behave elastically. So if we limit ourselves to the yield strength and then use our reductions, we won't get to that yield strength and we won't get into a point where we're permanently deforming. So the formula for determining this tensile load will be the area of the steel multiplied by the yield strength, okay? For the purposes of this class, we'll be using either grade 40 or grade 60 steel, okay? So F sub y is always going to be either 40 KSI or 60 KSI, or 40,000 and 60,000 PSI, if you want to think about it that way, okay? If we change how we're looking at this, instead of along the span, if we want to rotate our point of view and go back to looking at it along its length axis, if we have a beam that's B inches wide and D inches deep, okay? And if we have some area of steel, AS, could we determine what percentage of our beam is steel? How do you think we could do that?
You get your area of your beam and subtract the area of your steel.
Yeah. So you take your
Yep,
D times B minus the area of steel times D.
area of beam equals BD inches squared, right?
Yeah, well, if it's an inch, yeah.
Yep. And what did you say?
And then take BD minus AS times 3.
BD minus AS times 3.
If there's 3, you got 3,
Okay,
Steel
so
rod.
remember that this AS value,
is that the total?
it's our total area,
Okay.
okay? So it comprises all of this steel, okay? If I want a percentage though, what do we need to do?
Divide it,
Divide
BD by AS, or AS by BD.
AS by BD, yep. Does that make sense to everybody? See how we got to that point? Yep, okay. Now, we also need to figure out what is this compressive force? How can we model that? And what we're going to use is that C, this compressive force, is going to equal 0.85 F prime C. And the reason we don't want it to equal F prime C is if we use all of the capacity of the strength of our concrete in our design, what's going to happen? We could potentially deform it. We could potentially fracture it. We could potentially fail it. Okay? So we want to say that we're only going to allow this thing to get up to 85% of its design strength. Okay? We're not going to load it past that. Okay? So, if we wanted to look at what this moment arm looks like, the moment arm for our compression, we're probably getting a little congested, aren't we? I'll erase this stuff and we'll restart.
Where's the moment?
Our moment, so we're looking at the distance between our C and our T.
Okay.
Okay?
I'm barely treading water here.
I'm sorry. I forgot two terms here. B times A. Okay, so when we're using our compressive force, we have to assume that it's being extended over the entire width of the beam, right? And it's also being exerted over the entire distance, right? Because F prime C is in PSI, right? B will be in inches, A will be in inches, so that gives us a value of our C in pounds. C is now in pounds, T is now in pounds, so we're happy. We can evaluate them together, okay? So, our moment arm of C about T is going to be 0.85 F prime C BA times the distance, right?
Let's try that again.
Does that help? The compressive force C times some distance, right? And I'll change this to D actually, so that it's not confusing us with that D, right? So here we have some compressive force times some distance.
Wouldn't the distance be that little d though? Because we figured d is.
It wouldn't be the little d because little d is from here to here,
Okay.
right? So what's the distance? It's d minus the a over 2, right? Because this is the distance we want to measure. Okay?
That's what the d is though.
No, no.
He is from the top.
This d is the depth from the top of the concrete.
So the
To
big
the
D
middle of
is
the con-
d
to
minus
the
a
middle
over
of
2?
Yeah.
What's that?
So the big D stands for that equation right there?
Yes.
Okay,
Okay?
gotcha.
And C is going to equal 0.85 times your design strength, times your width, times your depth. Okay? You're just taking a stress, multiplying it by an area. By multiplying it by an area, you're now back into a load. Okay? A load times the distance gives you a moment. What about the moment for our tension? What's that going to be? What's the force component?
D.
Our yield? Yield. T.
T, right? Isn't that the force for tension? The tension in our steel
Times D,
times which D?
the big D.
Right. Okay? We're interested in how far away the tensile force is from the compressive force. Okay? So if we write out all our terms, 0.85 F prime C times B times A times little d minus A over 2 is going to equal our moment of compression. Our moment of tension is going to equal our surface area of steel times our yield strength
Times this D minus D, 9 over 2.
Yep.
A over 2.
That's an A.
Oh, that's an A.
That's an A.
That's a 9 is all.
If we want this beam to stay in place and to not fail, what do we know about these two moments?
They gotta be equal. or
They
at
gotta be
least-
equal and opposite in value, right?
Yeah,
So MC minus MT must equal 0. Or
didn't you say though MT could be greater?
MC, what's that?
I thought MT just had to be greater than MC. They should be equal to be perfect, but,
Our tensile force, yes.
okay.
Tensile force can be greater.
Oh, but for the moment,
Yep,
Okay.
from the moment to, yeah, keep in mind here, we're talking about moment,
Yeah,
okay?
I get it.
And we'll talk about it briefly, we're not gonna go into depth of multiple layers of reinforcement. One way that you can get around it, if you have a greater value of T, is you can put in multiple layers of steel. That will change your center of mass, but again, that gets us into a little bit deeper than we're going to have time to.
So the 0.85, that's a constant? That's the,
0.85 is a constant, yep.
that's always gonna be 0.85?
Yep, whenever we evaluate concrete from a structural standpoint, we want its capacity to be 85% of design strength. Yep, we don't want to exceed that. So, what do you notice about these two terms? What can we reduce if we're evaluating them? These are appearing in both of them, right? Okay, so that's going to remain the same. So we can write out that the area of our steel times the yield strength is going to equal 0.85 F prime C times B times A. Okay? And so this can help us determine a number of things, right? And we don't necessarily have to reduce. There will be times where we're going to need to know what that D is so that we can figure out what depth of that beam needs to be. But this allows us to figure out area of steel, compression zone, and it would allow us to figure out if we need to determine what the width of that beam would be. Okay? So we can write out that if we wanted to solve for A, the depth of that compression zone, it's going to simply equal AS times F of Y times 0.85 F prime C over B. Okay?
what's A?
A is the depth of the compression zone.
Alright,
Okay? The distance down into the concrete that we have compression.
How do you determine what that is? Or will that be a given?
If I wanted you to determine the depth of the compression zone, I would have to give you the area of the steel,
Okay.
the yield strength of the steel,
Sure.
design strength, okay? So as far as how structural engineers will actually determine it, at that point you'd figure out your compressive strength, you'd figure out the rate of depletion of that compression strength. You're going to move from compression to tension at some point, and you can figure out, just like we did with